Okay, good afternoon, everybody. Let's get started for today. So just a small set of reminders. We're not here on Monday. It's a day of observance, so we're not in Monday. Wednesday goes by your Monday schedule, which means there is a lab period on Wednesday because it's following the Monday class schedule. So those of you with Monday labs have to, well, you don't have to come. It was a good idea for you to come to your lab on Wednesday because that's going by Monday schedule. We have a problem session next week. We discussed that before. Hopefully that's going to be a good learning environment for you. So that's next week. Our term test one, I did find basically a typo on one slide in one of our lectures. The schedule on the syllabus is correct. Our term test one is Friday the 20th of October. So that confirms that date. Okay, any questions before we get started? Okay, so last day we defined and started talking about electric field. This was our slide we got done at the end of Wednesday's class. I just wanted to put a little bit of extra kind of summary on this slide. So we found a way to calculate the electric field at a point P, where point P is just some empty place in space. This big charge Q here is called our source charge. This is the thing that makes the electric field. So in our equation, let's just point at this equation. This is the electric field, and it is made by the source charge. This F, that's the electric force. This is the electric force felt by the test charge that's placed in the electric field. Okay? So this force is the electric force, and it is felt by the small charge Q. This Q here, this is the test charge, the one that is experiencing the force. So this one, it is important to include the sign of the charge. So our conclusion was that the magnitude of an electric field is K times Q over R squared. R is our distance between our point and our charge. And we see that our electric field points away from this positive source charge. And that's a true result in general. Electric fields point away from positive charges. So E points away from positive, or out of a positive charge. Okay, so that's a general result. Any questions there? Okay, so we'll do an example about that, and then we'll ask what happens if our source charge is negative, and then we'll keep going from there for today. So our example, I set it up to look a little bit like what we did in our previous derivation there. If you've downloaded the slides with a PDF, originally I had 50 nanometers. That made the electric field way too big, so I changed it to 50 millimeters. So you can go ahead and make that change if you've got the notes printed off there. So our first task is, let's find the electric field at point P. Our source charge is 1 microcoulomb. And our distance to our source to our point is 50 millimeters. So this is our distance R. We'd like to find our electric field. We should draw our electric field. We know that it points away from a positive, so we'll draw that field vector. Let's write down the equation to calculate the field. This will be pretty quick. So our electric field has a magnitude of K times the magnitude of Q divided by R squared. The direction it points is away, so 8.99 times 10 to the 9 newtons meters squared over coulombs squared, times Q, the magnitude of the charge, 1 times 10 to the minus 6 coulombs, divided by R squared, so 50 times 10 to the minus 3 meters squared. We get an electric field of 3.60 times 10 to the 6 newtons per coulomb. The direction of that vector will just say away. 10 to the minus 6, 10 to the minus 8, or sorry, 10 to the 6, 10 to the 7, 10 to the 8. Those are typical sizes for an electric field, so they're usually up around the millions somewhere. Okay, any questions here? This is kind of just a plug and chug. Okay, find the electric force on a proton placed at point P. So now in this problem, we're going to take a proton. In my picture, I'm just going to label it plus E, because I know my proton is positive. It has the fundamental charge E. We're placing it at point P, which is a distance r from the source charge. We want to find the electric force. Let's just draw the force first. The electric force is going to be a vector. This is positive, this is positive. Like charges repel, so our electric force points away. There are two ways to calculate the force. So one way is to go back to our Coulomb's law, which would say that our electric force is K times the charge on a proton times the charge of the source divided by r squared. It's repulsive, so the direction of that force would be away. Okay, so this is what we did in our last class and the one before when we talked about our Coulomb's law. There is a quicker way, or we can use the relationship between electric force and electric field. We know that electric force is the charge, the one that's feeling the force, the proton, times the electric field. A very common test kind of question is part A is you have this set of charges, find the electric field. Part B is find the force on an electron or a proton or something. So typically you'd find the field doing this sort of business and you'd find the force doing this sort of business. We'll do some examples as we go through class. So this F is on the proton. This charge is the proton. This charge is the field made by the source charge Q. Okay, so it's important to know what all of the things mean, otherwise it can get a little tangly. So the charge on a proton is plus 1.6 times 10 to the minus 19 coulombs. Our electric field is 3.6 times 10 to the 6 newtons per coulomb. It is a vector. I'll write my vector in words, which is away. That gives me a force of 5.75 times 10 to the minus 13 newtons away. So there's the force on a proton placed at point P. Any questions? Okay, the third bit of the example, find the electric force on an electron placed at point P. So in this one, we're putting in an electron, that's minus E. Cool. That's not showing up very well. What I wrote here on the page was minus E. An electron is negative, it has the fundamental charge. Negative E. Sorry, I didn't realize it would look so poor on the screen. So we'd like to find the electric force. Let's draw the force. This is positive, this is negative. The force is attractive. So there's the direction of the force. We can use our Coulomb's law, K times Q1 times Q2 divided by R squared, where the direction is towards. Or we can use that our force is the charge of the electron times the electric field. So the force on the electron is the charge of the electron times the field the electron is sitting in. Charge of the electron is minus 1.6 times 10 to the minus 19 coulombs times the field, 3.6 times 10 to the 6 newtons per coulomb. As a vector, that direction is away. Okay, so now we have to think about the vector stuff. The number part is easy. So I've got our minus sign here. Multiply the numbers, minus 5.75 times 10 to the minus 13 newtons. So negative of away. That's sort of a weird wording, right? So let's think about it in terms of something else. If our vector pointed right, that would be the positive x direction, right? What would the negative x direction mean? to the left, right? So the negative of a direction just means the opposite direction. Okay, so the negative of away means the opposite direction. So 5.75 times 10 to the minus 13 means toward. So the negative away means the opposite of away, so towards. So one result we'd like to point out here on this slide is when we have a proton, when our charge that we place here at P is positive, the force and the field are parallel. So if our test charge is positive, force and field are parallel. So if our test charge Q is positive, force and field are in the same direction. If Q is greater than 0. Okay, so if your charge is positive, the force and the field are the same direction. If your charge is negative, if Q is less than 0, F and E are opposite directions. And that comes out when we include the sign of the charge in our equation down below. Okay, any questions? So that's our example when we have a positive source charge. Let's look at what happens when we have a negative source charge. Probably you have an idea. We can maybe move through this a little bit more quickly than the previous stuff. So find the electric field at a point P near a source charge, negative Q. So sometimes these charges are negative because charges are allowed to be positive and negative. Both kinds of charges make electric fields. So very quickly we'll recap. So we picked some empty point in space P with a distance r from the source charge. So Q is the source. And our goal is to find what is the electric field right here. We're going to follow the same procedure. We're going to place a small positive test charge at point P. So right here at point P, I'm going to put in a charge that is plus Q. I'm going to ask, does it feel an electric force? The answer to that question is yes, it feels an electric force. That force is towards the negative charge because we know that opposite charges attract. That's our distance r. Our force is towards the source charge. The force has a magnitude of k times the magnitude of this charge times the magnitude of this charge divided by r squared. And the direction is towards the source charge. So this is what we did when we talked about our positive source charge. We asked, does it feel a force? The answer is yes, towards the source charge or attractive. Can we write down the magnitude of that force? Yes, because we know Coulomb's law. So that's what we've done here in this step. Our third step, we take away our test charge and we ask what is the electric field left behind. So the electric field is the force divided by our charge Q. Electric field is the electric force divided by our charge Q. This charge Q is our test charge. It is positive. Q is greater than 0. Therefore, E is parallel to F. They're in exactly the same direction. So we can draw the direction of the electric field. So our electric field has to point towards the source charge. The magnitude of our electric field is the magnitude of the force. So K times the magnitude of Q times the magnitude of the source charge divided by R squared divided by the magnitude of the charge. So the magnitude of the field is the magnitude of the force divided by the magnitude of the charge. These guys cancel. And we're left with that electric field created by the source charge has a magnitude of K times the magnitude of the charge divided by the distance from the point to the charge squared, and the direction is towards the source charge. So our conclusion here on this slide is that if our source charge is negative, the electric field points in towards the negative. So it's out of a positive and towards a negative. So electric field points into a negative source charge. So that is something that you are expected to remember. What's the direction of an electric field around a charge? You have to remember out of positive and into negative. That's not something I'd tell you if you asked on a test. So you got to remember that little bit. Okay, questions here? Okay, let's quickly go through an example. So there's the idea. And we'll go through an example like what we did with the positive source charge. So I've got a source charge of minus 2 microcoulombs. I've got a distance to a point, 25 millimeters. Again, if you downloaded or printed the notes, that used to be nanometers, now it's millimeters. We'd like to find the electric field at point P. First thing we'll do is we'll draw the electric field. We know that it points in towards a positive. So there's our electric field. Our electric field, E, is K times the magnitude of the source charge divided by R squared. The direction is towards the source charge. Put in our numbers, 8.99 times 10 to the 9 Newton meters squared divided by Coulomb squared, times the magnitude of our charge, so a positive 2 times 10 to the minus 6 coulombs, divided by the distance squared, 0.0250 meters squared, gives us an electric field of 2.88 times 10 to the 7 newtons per coulomb towards the charge. So there's our electric field. Find the electric force on a proton placed at point P. So we're going to put a proton here, plus E. That one showed up okay. This is positive, this is negative. The electric force is going to point towards. So our electric force has a magnitude of the charge on the proton times the magnitude of the electric field. Or as a vector, this way. So the charge on a proton is plus E, so 1.60 times 10 to the minus 19 coulombs times 2.88 times 10 to the 7 newtons per coulomb gives us a force of 4.60 times 10 to the minus 12 newtons, and the direction is towards the source charge, negative Q. Okay, so there's the force on a proton. Last, we'd like to do the force on an electron. Our electron is negative E. I think that showed up okay, negative E. This is negative, this is negative. We know that the force is going to point away. So our force is equal to the charge of the electron times the electric field, minus 1.6 times 10 to the minus 19 coulombs, times 2.88 times 10 to the 7 newtons per coulomb, gives us an electric field of 4.60 times 10 to the minus 12 newtons. The direction is away from the charge. So if you were following the vector through, it would be minus a towards, which is the same as away. Okay, any questions here? So the next page in the notes is more or less a study slide that I made up for you. So it's a summary of all the key points that we talked about. I'll post that one with the notes. All that stuff is in your book too, of course, but I thought you might like to have sort of a concise one typed up in your notes for you to go back through as you study. So now let's do the kind of problem that you are most likely to see. So this is a super typical kind of problem. I have a set of charges. Part A is find the electric field at some point that I show. I've shown this point to be at the midpoint on one side of the square. So the first is find an expression. That means first we're going to do the problem in all symbols. Part B, we're going to pop in some numbers. Part C, we're going to find the force if we put a charge at point P. This is super typical, you know, this kind of idea shows up again and again, so this is going to come back. So important here, did I get my slides out of order? I'm sorry, I put my slides out of order when I put them together. That one has 4 charges. Let's do the one with only 2 charges first. So sorry. Okay, yeah, 4 charges, we can do that, no problem, but let's start a little bit easier. Let's do the one with 2 charges. So I just want to go back to this slide. I just had them out of order for a second. Same sort of deal. You want to find the electric field at point P, and we want to find the force on a proton if we place it at point P. I've made my diagram really nice and big so that we can see all the steps clearly. In this problem, if we're just making sure we know what's what, Q1 and Q2 are the source charges. These are the 2 things making the electric fields. What we're going to do in solving part A is we're going to find the electric field due to Q1. We're going to find the field due to Q2. We're going to remember that those are vectors, and we're going to do the vector sum to find the total field. So that's where we're going with this. And that's what I've got up here in my process box. So this shows us where we're going with this. So step 1 is draw the electric field vectors at point P. I'm going to give you a minute to draw those for yourself first. It's really important to get those right, and it takes a lot of practice. So here's a moment for you to get some practice, and then we'll do them together. Okay, so probably you've got those vectors drawn. So the electric field at point P because of Q1, so when we're drawing the field due to Q1, we can forget about Q2 for the moment. Okay, so we're only looking at Q1 first. Q1 is a positive charge. What we know is that electric field points away from a positive. So we put our pen on top of point P and we go away from a positive. There is our electric field E1. We should label that field E1. Our electric field due to charge 2. Charge 2 is negative. You can forget about Q1 for the moment. We know that electric field goes towards a positive, so we put our pen on top of P and we go towards the positive. And then we'll label that one, that's our E2. Okay. Your vectors do have to come out of point P. The tails of the vectors should be at P, and you take your vectors from there. If you draw them anywhere else, it's probably not right, and you're probably going to get confused from your answer. So they all got to be drawn from point P. Okay, that's step 1. Step 2, let's find the magnitudes of our vectors. So the magnitude of the vector, we know is KQ over R squared, so we'll start with that. So the magnitude of E1 is K times the magnitude of Q1 divided by R1 squared. As soon as we write down R1, we do need to identify it in our diagram. R1 is the distance from our point to our charge Q1, so that's our 1.5 millimeters. So now we can put our numbers in, 8.99 times 10 to the 9 newtons meters squared over coulombs squared, times the magnitude of our charge. 1 nanocoulomb is 1 times 10 to the minus 9 coulombs, divided by r squared. 1.50 times 10 to the minus 3 meters squared. Through the calculator, and we get that the magnitude of the field is 8.99 times 10 to the 6 newtons per coulomb. This is going to be a vector problem because electric fields are vectors. We care about the vector components. So let's go, we know we care about the components, so let's go ahead and find the components of E1 and E2 right now. For our components of E1, we see that it points straight up. It doesn't point left or right at all. So the x component of E1 is 0. So E1x equals 0. E1y is the whole thing, 8.99 times 10 to the 6. Okay, so we've got the magnitude of E1 and we've got the components of E1. We're setting ourselves up for success here. Now let's do E2. We'll find the magnitude and we'll find the components. So for the magnitude of E2, it's K times the magnitude of Q2 divided by R2 squared. When we write R2 on our equation, we have to put R2 on our picture. R2 comes from our point to our charge Q2. Here's R2. We don't know R2, but we see that it's the hypotenuse of a right angle triangle, so we can use Pythagorean theorem to find our R2. R2 is going to be the square root of 2 millimeters squared plus 1.5 millimeters squared. Through the calculator, and we find that to be 2.50 millimeters. Okay, so there's our R2. Now we're all set to find the magnitude of E2. Put our numbers in here. Remember, when we're finding the magnitude of the electric field, we use the magnitudes of the charges. That means we use the positive values of the charges. So 2 times 10 to the minus 9 coulombs, divided by our distance squared. Put that one through the calculator. The magnitude of E2 is 2.88 times 10 to the 6 newtons per coulomb. We do need to find the components of this. The components of this one are not quite as easy as E1, but components shouldn't be too much trouble for you. So the x component is the part that's horizontal. So there's E2x. The y component is the part that's vertical. There's E2y. If we want to find our component, we need to use our trig, so we have to find theta. If this angle is theta, then this angle here has to be theta, because it sort of makes like a little Z. Those are parallel lines, one of those high school geometry things. If we want to find theta, there's our angle. We know the opposite and the adjacent, so we can use our tan function to find theta. So tan theta is the opposite, 1.5 millimeters, divided by the adjacent, 2 millimeters. Theta will be the inverse tan of that. Put that through the calculator and we get an angle of 36.9 degrees. So there's our angle theta. Now we can use our sine and cosine to find our components of E2. So E2x points to the right, so it's positive, plus E2 times cosine, 36.9 degrees. So our x component of the electric field E2 is 2.30 times 10 to the 6 newtons per coulomb. Our y component of E2, E2y, it points down, so it has to be negative. It's opposite the angle, so we have to use sine. So our y component of the electric field E2 is negative 1.73 times 10 to the 6 newtons per coulomb. Are we good to hear? If you're a little bit rusty with your vectors, there is a vector review posted up on Brightspace. You can have a look through that. Or you can drop by and see me. I don't mind going through vectors with anybody. Okay, so we're following our process really well. We found our magnitudes, we found the components. Now we have to do our vector sum. So our total electric field, E, is E1 plus E2. Our total x component, EX, is E1x plus E2x. So I've got 0 plus 2.3 times 10 to the 6 to get 2.30 times 10 to the 6 newtons per coulomb. EY is E1y plus E2y. 8.99 times 10 to the 6 minus 1.73 times 10 to the 6 to give us 1.15 times 10 to the 6 newtons per coulomb. Okay. So there are the x and y components of the total electric field. Almost finished. To finish your problem, you do have to write your answer as a vector. So the electric field is the x component, 2.30 I hat, plus the y component, 1.15 j hat, times 10 to the 6 newtons per coulomb. So there's our electric field vector. If you're someone who doesn't really like the unit vector notation and you prefer to give it in the polar notation, you might go ahead and find that that was 2.57 times 10 to the 6 newtons per coulomb at 26.6 degrees above the x-axis. If you gave your answer in that notation, that's fine. For me, I would probably always stop with unit vector notation, because then I just don't have to do the extra work to find the polar notation, but up to you. If you like it better, that's fine. Okay, there's part A. Like I said, this is a pretty common problem, and this is the method. If you follow these steps, on your assignment, the test, you'll kind of always get it right. The worst you'll do is a calculator mistake, which is not a big deal. Part B, find the force on a proton if it's placed at point P. So part B is next. So we're going to put a proton right here. So we've got plus E here, we've got Q1 here, and Q2 here. We want the force on that proton. There are two ways to do it. The long way is what we did in class a couple of days ago. We use Coulomb's law to find the force vector here. Coulomb's law to find the force vector here. We find the components of those force vectors and we do the vector sum to get our answer. That is a perfectly legitimate way. Somebody's phone going off? There's somebody's phone is making noise. Okay. So that's a perfectly legitimate way to do it. If you do it though, you're just sort of doing more work than you really have to. So it's not wrong, but it's not the fast way to do it. You can also do that your electric force on our proton right here is the charge of the proton times the field it's sitting in. Okay, so this is the quick way to do it. So we take our proton charge, 1.60 times 10 to the minus 19 coulombs, times the electric field that we just found. And we get our answer for our force, 3.68 plus 1.84 J times 10 to the minus 13 newtons. Okay, so that's kind of the quick way to do it. Any questions? So a couple of classes ago when we used Coulomb's law to find our forces, this was the structure of the problems. So both field and force have the same structure when you're going through the work. That's kind of a good thing. I would caution you to make sure when you're doing problems, you understand, are you asked for electric field or electric force? Lots of times people get them confused. So you might be asked for electric field and you find the force instead. So make sure you just don't get them mixed up between force and field and which equation is which. Okay, now let's do our 4 charges on a square. So we want an expression for the electric field at point P. We'll use symbols. Then we want to find a value. Then we're going to put a charge there and find the force. So our steps are going to be the same. We've got 4 charges. These 4 are the 4 source charges. They're each going to make an electric field. We're going to find the magnitudes, find the components, do the vector sum. So that's where we're going with this. So charge 1 is plus Q. I'd like to draw my electric field E1. So for my electric field E1, my charge 1 is positive, E1 has to point away. So here is my vector E1. I can feel that my handwriting is about to get tiny. I'm going to zoom in. So there's my field E1 pointing away from charge Q1. My electric field E2 points away from charge Q2 because Q2 is positive. Here's my electric field E2. My electric field E3 points into charge Q3 because Q3 is negative. So here is E3. And my electric field E4 points into charge 4 because charge 4 is negative. So when you're drawing these vectors, you've got to remember what happens around the positives and what happens around the negatives. Any questions here?
Just like recap, I guess the point P, is that presumed to be positive?
Point P is an empty point in space. There is nothing at point P.
Okay, so then at that point, so the electric field just goes towards what it's attracted to?
So electric field points towards a negative and away from a positive.
Okay.
Yeah. Yeah, that's the key bit to remember. So our deal here, you might start to recognize the symmetry right off the bat, maybe you won't. We're going to follow the method, and then we're going to take ourselves through it. Yeah?
Do the electric forces for E3 and E4 cancel each other since it's negative Q and Q up and down?
Okay, so there's a good point. The symmetry in this problem is that E3 and E4 are going to sum to 0. They're going to cancel each other out. The y components of E2 and E1 are going to cancel. The x components of E1 and E2 are going to add up. So that's what we expected as the symmetry of this problem. If you jumped right to that and wrote it down, that would be fine because you can see that it's true. But we'll go through the process anyway because the process is kind of important. So let's write down the magnitude of electric field E1. So the magnitude of field E1 equals K times the magnitude of Q1 divided by R1 squared. R1 is from charge 1 to my point. There's R1. We want to find the length of R1. This side is L over 2. This side is L. R1 squared is L squared plus L squared, L over 2 squared. L squared plus L squared over 4 equals 5L squared over 4. Right, so we're sticking with some symbols here, some fractions. I guess if you wrote 1.25L squared, that's okay too. I'm much more of a fractions person. So let's put these things in right here. I've got K times Q over 5L squared over 4. 4 times K times Q over 5L squared. I'm doing this one in symbols first because it's really common to have problems where there's only symbols. I know students hate it, but we'll do some practice in class and then hopefully it won't be so bad on the test. Let's get our components. So to get our components, we're going to need an angle. I'll call this angle theta, which makes this angle theta. To find my angle theta, we know that we could do the inverse tan. I don't want to get a number just yet. So my E1x is equal to E1 cosine theta equals E1, which is 4 times k times q over 5L squared. Cosine theta is opposite over cosine theta is adjacent over hypotenuse. So it's L divided by R1. So L divided by root 5 times L over 2. Or 2 over root 5. Okay, so I found an expression for my cosine theta. Times 2 over root 5. So my E1x is 8 times k times q over 5 root 5 L squared. Okay, so there's an expression for my x component of E1. My y component of E1 points down, minus E1 times sine theta. Got my expression for E1. I'd also like to have an expression for sine theta. So sine theta is opposite over hypotenuse, L over 2 divided by R1. So this turns out to be 1 over root 5. So negative 4 times k times q over 5 root 5 L squared. So there are my components, E1x and E1y. For E2, let's use some symmetry here. So E2, this is R2. R2 equals R1. This angle theta is the same. This tells us that the magnitude of E2 is equal to the magnitude of E1. 4k times q over 5L squared. E2x is the same as E1x. E2y, that one points up where E1y points down, so they're just opposites. Okay, so for this bit, we're applying the symmetry that we can see in the problem. Is that bit of symmetry okay? People can see that? It's the same distance, same angle, same charge, so it has to have the same values. So that takes care of E1 and E2. E3 and E4 next. Grab a fresh sheet of paper. So the magnitude of E3 is k times the magnitude of Q3 divided by R3 squared. R3 is from here to here. R3 is equal to L over 2. So I've got k times Q divided by L over 2 squared. So I get 4 times k times Q over L squared. E3 points straight up, so E3x equals 0. E3y is the whole thing, and it's positive because it points up. For E4, we can use our symmetry again. E4 and E3, they're the same distance away. Neither have an x component, so the magnitude of E4 is equal to the magnitude of E3. E4x is 0 because it doesn't point left or right. E4y is equal to negative 4kq over L squared. Okay, so there are all the components in all the symbols. We're asked to find an expression for the total electric field. That means the vector sum. So we've got to add up all the x components and add up all the y components. So our total electric field E is the sum of all the individual fields. So EX is E1x plus E2x, plus E3x, plus E4x. So we're gonna add E1x to E2x, E3 and 4 have 0x components, so we'll add those two things up, and it gives us 2 times E1x, or 16 times k times q, 5 root 5 over L squared. So that's the x component of the total vector. The y component of the total vector goes right to 0. So for E1 and 2, those y components cancel. We saw that in our components that we wrote down. E3 and 4, those cancel, so the net y component is 0. We write our electric field as a vector. We've got the x component, 16 times k times q, 5 root 5 L squared, points in the x direction, so we put an I hat on there. Okay, so that's how you would go through a problem with just symbols. You keep going using all the symbols you're given, and you just simplify the fractions as much as you can. Part B says put some numbers in. So there's our expression for our electric field. It says find the electric field if we know L and we know Q. So E is 16 times 8.99 times 10 to the 9 newtons meters squared over coulomb squared. Q is 5 times 10 to the minus 3 coulombs. Divide that by 5 times root 5 times L squared, 0.0375 meters squared in the x direction. That gives us an electric field of 4.57 times 10 to the 10 newtons per coulomb in the x direction. Okay, so for part B, we get to put our numbers in and find the total field. Part C, again, this is following the typical format. We're placing a charge at point P and we want to find the force on it. So all we need to do here is F equals Q times E. We include the sign of our charge, so this is the force on Q. E is the field made by the source charges. So negative 0.5, the microcoulomb, that's 10 to the minus 6, times that field, 4.57 times 10 to the 10 newtons per coulomb, I hat. Put that through the calculator, and what we get is minus 2.29 times 10 to the 10 newtons I hat. So there's the force we would get in that electric field. Again, the longer way to do that problem would be to place the charge here, draw the 4 force vectors, find the 4 components, 4 sets of components, and then do the vector sum. We have a tiny bit of time left, but this really feels like a place to quit. Yeah. Okay, so we'll stop there for today. The last one was kind of a lot. Any questions? Yep.
Would you be able to just say to the right?
To the right is fine, yeah.
And also, is it fine to only use symbols if you, even if you were given the, like all the numbers from the beginning and then just plugging in the symbol,
Yeah. That's A-okay. If you're a symbols person, you can keep symbols right to the last step. It's the way I do things.
You don't have to worry about a 6 days.
Yeah, absolutely.
Yeah, I was wondering about that.